Part three of the weekly discussion of seminar events that I attended. I'm in a sabbatical period here at Stanford, and I'm discussing events that I attend, seminars, colloquia, events, lectures, all kinds of things. This is the third installment of the week. I've already had two parts, one about robotics and one specific about geometric algebra and the application of geometries and symmetries to data analysis, in particular efficient inference. This third part is a general overview over other events, not that they're less important or anything. Some of them are actually super interesting, but I thought just this grouping would make more sense also from my perspective and from my focus, and hopefully also for the listeners. This is the Not Even Wrong podcast. It's November 12, 2023. This is Krim Delco. For the year, we're up 88.3%. The market's up 14.8%. We're outperforming by 73.5%. So the first event I want to talk about is a philosophy event. Edward Slingerland presents his views on Confucius and the role of perception and literature on morals. In other words, he talks about this Chinese philosopher Confucius, which is instrumental in the Chinese psyche and the Chinese philosophy, very similar to the Christian belief in the Bible and the form of the civilization, the Western civilization, which is based on Christian thought, Christian values. This is very similar, and Slingerland talks about the influence that literature has on the moral compass of people. And I ask myself, well, how's the other way around? How does action, literature drives action? So there's almost like there's the fundamental thesis of biology. You know, we have DNA, RNA, protein. Here we have literature, action, and then literature. So there's a circular reference here. I think what I thought was most interesting actually in this lecture, two things. One, I asked Slingerland about AI, and he said that the only way he sees intelligence being influenced by literature, or literature actually influencing intelligence, is if it's embodied. So we're talking now about robotics. You know, the conference on robot learning, this also last week, I'm going to, by the way, talk about this separately, but in that conference, we definitely had lots and lots of discussion about literature and about words and about large language models and how they impact robot learning. And this is really very interesting how this borders cross between philosophy and literature and AI. And you know, like I said several times already on this podcast, whenever I'm involved in a discussion about artificial intelligence, deep questions of humanity come up. And when I talk about deep questions of humanity, artificial intelligence come up. So there's this circle that is closing, and I thought it was really interesting. Now, another interesting comment that was made by one of the attendants was the difference between Confucius and Laozi. And I think that's another really interesting just tidbit here, or not even tidbit. This is more deep. There's more depth to this, because we have Confucius, which defines a way of life, a set of moral values, as a set of rituals and rules. And Lao Tzu is more about the essence of things. So it's a lot more concise. It's a lot more deep. And if you look at sort of, if you want to put this in technical terms, we have Confucius, which is the equivalent of symbolic systems, differential equations. We try to explicitly define the system, versus Lao Tzu, which is a lot more the essence of things, which I would say reflects large data models, large data effect, machine learning based on large data to find the essence of things without us maybe even knowing what they are. But we follow the essence of things. And I asked Slingerland what he thinks about AI. He said, again, intelligence has to be embodied. And I thought this was really interesting for several reasons. I think one, it opens the question of Confucius versus Laozi. and beyond the political implications that Confucius has, because Confucius is also politically very convenient for the Chinese Communist Party. He defines a very precise set of rules of how one should live, which is exactly how the Chinese run their society. And Laozi would be the exact opposite, more sort of the Western ideal of the essence of things, the organic growth of nature in form of liberty, which is one of the manifestations. The next seminar I want to talk about is physics. Adam Kaufman from the University of Colorado Boulder, he talks about using nuclear spin for quantum information. Now, this is very similar to Vladan Vuletic's presentation, where we use nuclear spin for quantum information processing. And what they both have in common is the Rydberg state, where you separate an electron far from the nucleus so you can then isolate the nucleus and the spin and use it for study and measurement and manipulation and of course quantum information, because the coherence time is very long. Certain materials are being used. Ytterbium 171, doesn't matter what exactly the material is, but I think what's important here is that we have this idea that we can use properties of the nucleus, not the whole atom, and not sort of make it chemically less active by separating the electron, not taking it away. This is not an ion. This is just an electron in a different energy state, which isolates the nucleus and gives the spin a potential for quantum information. This is the way I understand this. Kaufman seems to be very active. He's a young researcher with lots of accolades, so that's something. He works with JILA, the Joint Institute of Laboratory Astrophysics. That's a collaboration between the University of Colorado and the National Standards Board. So he's active in that sense, and I think lots of interesting physics comes out of Colorado, in particular atom computing, which uses Rydberg states and nuclear spin for quantum computation. Another topic that Kaufman was talking about was using laser tweezers to optically trap the nucleus and then manipulate it. And lastly, also they're using a lot of identical bosons as a sort of collective quantum system. And there's also the Vuletic concept of the entanglement plays a role here, and the ability to measure things more precisely because you use entanglement. And then the question comes up, why can one measure things more precisely with entanglement? And one of the things Kaufman says is that one of the things, so the reason we are so excited about quantum manipulation and quantum information is we can get faster results and more precise results. And to me, that's kind of a philosophical question, of course. Why is it that we can get more precise atomic clocks if we use spin squeezing, for example, and entanglement as a tool? Is it because we have massive parallelism? Is it because we are literally using computation from the multiverse? Or those sort of questions come up. But I think to summarize Kaufman's talk, it's really about using nuclear spin. It's about using a manifold of bosons, certain materials that have this bosonic character of spin equals 1, that then as a whole create a quantum system. And with very high coherence times, they seem to be better than, let's say, other ion traps or superconducting materials and those sort of things which are being used. But this is just another form of physics that is being used as a substrate for quantum information. within that spirit, there was a seminar in the Q-Farm series. Charles Marcus, I would say pretty accomplished physicist. He was at the Niels Bohr Institute in Denmark. He's a graduate from Stanford and now is at the University of Washington. He creates Majorana electrons by bouncing quantum dots off superconductors. Now, that is in itself a very difficult, experimentally challenging process, and Marcus spoke about the actual implementation, the way they do it, the way they manipulate these electron billiards, as they call them. I think the way I understand this is you have let's say a superconductor, and then you have a quantum dot that bounces off that superconductor, and that creates dynamics between electrons, and that creates the Majorana electron, which is an electron that is also its anti-electron, and that allows for things like non-abelian statistics, so the non-commutative. So if you have electron 1 and 2, and then you put 2 in front of 1, that changes the whole physics. So it's not it doesn't commute. You have the ability to create more robust topologies that can be used for quantum computing. This is definitely way over my head. I don't want to talk too much about this because I'm not familiar with it, but the way I understand his talk is create the quantum dot, bounce it off a superconductor, observe Majorana zero modes or Majorana electrons, and then use them for quantum computing. And I think what was interesting here is that we really are exploring very interesting physics for quantum computing. That's one thing. The other is the real, like the sheer technology, just the technological advancements that are necessary to manipulate these things are amazing. And I think Marcus is a good example of somebody who pushes the boundaries and is also able to sort of still tie it together to the application level, and that's what impressed me about this talk. The third physics talk I attended this week was Christoph Naegerl from the University of Innsbruck. Now, Innsbruck is a powerhouse in quantum physics, in condensed matter physics, and also in search for new physics through quantum material, manipulation of quantum materials. So what Naegerl was presenting is ultra cold cesium that is being confined from 2D to 1D, so in one-dimensional space, two-dimensional space. This creates new physics, interesting physics. One of the most interesting things that Naegerl discussed was the way to even measure, let's say, temperature of 1 nano-kelvin and things along those lines, which is really amazing. The way they measure this is they look at certain frequencies of vibrations, and then they compare that to, let's say, where they theoretically should be, and that's kind of how they get a sense for the temperature, because there is no other way to measure. And the question then is also, what exactly is measuring the temperature? Which instrument? What is temperature in that sense? Of course, in sort of general physics, temperature is speed. So when you have something at 1 nano-kelvin, then the speed slows down, and that's kind of how you measure, let's say, frequencies or the speed by which something vibrates. That's how you get a sense for temperature. Naegerl talked about taking a boson, like a certain cesium isotope which has bosonic character, confine it, ultra cool it, and then measure the temperature, find out that ultra cooled boson actually doesn't condensate. It acts like a fermion, which I don't understand what that exactly means, but it just says that there's some interesting physics going on. And then he also studied how impurities go through a material like this. He found out that those impurities have anionic properties, so they become quasi-particles themselves. And another thing they did, they were able to create Bose-Einstein condensates other than in the ground state. I think, again, to me, these are all very difficult concepts to understand. But I would say what's interesting about Naegerl is the experimental nature of his work. It's really hands-on, try-error engineering. It's real experimental physics. So I got a good sense for what an experimental physicist actually does. Measuring temperature, for example, creating a Bose-Einstein condensate that is not in the ground state. So create something new. And then the impurity, like induce an impurity into, let's say, this superfluid type, supercooled boson, and see how it acts, and it acts like a quasi-particle. Naegerl works at Innsbruck, which is a stronghold for experimental quantum physics. He seems very hands-on. When introduced by Benjamin Lev, who organized a seminar, Ben said that Christoph taught him electronic when he was a Caltech postdoc. Ben got his PhD from Caltech, so there's a little bit of context there. The next talk is within computer science and image recognition. It's actually part of the signal processing seminar, and it's Adil Jalal from UC Berkeley. Now, he is trying to solve the problem of compressed sensing. So you have very little data, and you use generative models to reconstruct the actual reality. So this is his work. It is being applied at MRI. He presented some theoretic work, which has to do with Lipschitz and certain assumptions of what kind of information you're looking at, and if it's n Lipschitz, then you can sort of all you need is something log n type data to reconstruct the picture. So there's some theoretical groundwork being done in terms of how much data do you actually need minimum to be sure to reconstruct something at a certain level, and then you can use generative models. So you can learn from in sort of a generative model type way how to regenerate those pictures and then use it in things like MRI or astrophysics. I think the interesting thing about Ali Jalal's presentation was that he works with, he's trying to reconstruct images from very little data. And he's trying to do it in a new way. He talks about the old way, which used sparsity. Again, those are concepts I'm not very familiar with. And the new way is generative data. The way I understand it is that you can train a model in abstract. So he said, for example, in the presentation, that if you train, you sort of find the essence of an object. And this goes back to even Suzhong and the idea of objects having a certain geometry, of a certain fundamental essence, even Laozi. I mean, you can even be philosophical here, but anyway, let's get back to Adil Jalal. So we have every object has a certain essence, a certain set of vectors that define the object, and a generative model can learn that, and then you can take a random, let's say, a generative model can learn the essence, let's say, of human brain, and then if you have a certain amount of data from, let's say, Louise's brain, you can reconstruct that brain with the generative model from that has been learned on many other brains. So that's the fundamental idea of this presentation. The next presentation I want to talk about is from the economics department. It's Dave Donaldson, MIT, former Stanford, a paper on misallocation. Now, what is misallocation? What does that even mean? How do you measure that? It's an econometric paper. It's a model paper. It's lots of math here, but let's just leave it at a very high level here. First, what is misallocation? It just means that we have an economy with firms and they produce, and somehow resources are not optimally distributed. And the way you measure that is when you have a demand shock. So when something changes, let's say there's more demand for firm A, the firm A has to change its input. That's the way Donaldson measures misallocation. So when you have, if you think about it, let's say you have an economy, let's say you have, Fremont is a small economy, you have a bunch of factories there, they produce things, and then one of the factories has to expand to satisfy demand. That means that prior to that demand happening, there was a misallocation of resources. There should have been more resources available to that firm. That's kind of the way I understand it. I have to say, it was definitely it wasn't a good seminar in a sense that they used a lot of jargon and very little common sense. I would say Donaldson is probably one of those nerdy type professors that knows his thing but is not able to communicate it properly. So I wouldn't want him as a teacher. And I thought in general, I wasn't able to get, like when I attended the seminar 2 weeks ago about industrial allocation and flexibility of resource planning, that was very technical and very math intensive, but I still understood the fundamental concept and the application. Here I didn't. So I was definitely taken aback by this seminar. I thought that Donaldson was trying to impress his former professors at Stanford more than anything else, which was disappointing. But I guess that's part of the academic game, and I don't want to judge that. But again, to me, this wasn't enormously useful. So lastly, I want to just mention Fei Fei Li's book party that I attended, The World's I See, her new book.